Welcome, everybody. It's my pleasure today to introduce Nicolò Zava, who will tell us about Gromov-Hausdorff distance to compare chromatic metric spaces.
Thank you very much, Henry. Thanks to all the organizers and the selection committee for the great opportunity of presenting my work here. This is a joint work with Ondřej Draganov. I always butcher his name. I apologize. And Sophie Rosenmeier. Unfortunately, there is no preprint yet, but we plan to submit something on arXiv in the following few weeks. So you can refer to that in the future. Okay. Compare shapes, Gromov-Hausdorff distance. So many data sets can be naturally seen as metric spaces. You can imagine point clouds, Riemannian manifolds, lattices, and so on and so forth. We have in the geometry backpack the Gromov-Hausdorff distance as a notion to compare metric spaces. This was introduced by Gromov, and some earlier works can be traced back to Edwards' work and Cadet's. It measures how different two metric spaces are. It has very nice properties. It allows for comparison between continuous and discrete objects. From the topological point of view, this is absolutely especially like general topological point of view, this is absolutely non-trivial. It precisely captures isometries between spaces. It is a variant under rigid motion. It is stable under small perturbation, meaning that if you have two metric spaces that are somewhat similar, you just move the points a bit, then their Gromov-Hausdorff distance is small. Another very important property is that it doesn't depend on where these spaces are. You can imagine, okay, I have a point cloud, a finite subset of Rn, and I want to compare two of these. With the Gromov-Hausdorff distance, you can do it in such a way that it doesn't depend on the fact that you are realizing it in Rn. And of course, it has, it's called distance, so it has nice metric properties. Also, the space of all compact metric spaces have nice metric properties. Not everything is positive. It's a nightmare to compute. Even like simple sub-problems are almost immediately NP-hard. However, it provides a very useful theoretical framework to discuss shape comparison. And this line of research can be traced back to the work of Memoli and Sapiro. So where does it fit? This is the standard computational topology pipeline. From a data set, you extract topological signature, you then vectorize, and then either perform analysis or feed these data to some machine learning algorithm. Well, you want that all these passages to be stable. What do I mean by that? Small perturbation in the data set or in the topological signature shouldn't drastically change the outcome. In other words, if two data sets are similar, so should be their signatures. Otherwise, it's absolutely of no use, because if you think of situations where if you move a point, then the topological signature completely differs, then it's too sensitive to errors to be applicable. So if two data sets are similar, where in the situation where we work with data sets that can be represented as metric spaces, you can use the Gromov-Hausdorff distance. So we can write some stability results. Of course, these are not the only stability results you can find in the literature, but you can use the Gromov-Hausdorff distance to show stability of certain topological signatures. Starting from the very silly example of the diameter, you erase everything, you just save the diameter of a metric space. The difference between two diameters is bounded by twice the Gromov-Hausdorff distance between the original metric spaces. More refined, the victorious persistent diagrams are also stables in this sense. Mind that this may not be obvious, but if you have small Gromov-Hausdorff distance, let's work with the Vittori's-Rips persistent diagrams. If you have small Gromov-Hausdorff distance, then it means that the topological signatures are at most that close. At most that far away, sorry. So another advantage of studying the Gromov-Hausdorff distance is that if you study the geometry, you may find theoretical obstructions to the construction of certain invariants with good distortion. There may be some subspaces inside the Gromov-Hausdorff space that are that cannot be deformed into, for example, Hilbert spaces. But this is not what I want to talk about. So we have shapes, and I guess that most of you may think that they kind of resemble each other's. Maybe 7 is a bit of an outlier. It's like slightly different, but all of the others look like circles. Well, what happens if we add informations to the points? Information in the form of colors, but of course you can imagine information also in the biological sense. If you have that points represent cells of different kinds, and then maybe your judgment has changed with the addition of colors. Actually, maybe you thought 7 was far away from the others. Now maybe the distance between 5 and 7 should be somewhat smaller than the distance between 5 and 2, because they have like the red spots in the same position. So this is what I want to discuss how to generalize the Gromov-Hausdorff distance to this setting. And see, so this is the outline. First, I would like to introduce formally what I mean by chromatic metric spaces, introduce the C-constrained Gromov-Hausdorff distance, and then validate its definition by showing the stability of the six-pack, which is a topological pipeline to extract cis-persistent diagrams from chromatic point clouds. Let's start with point 0, because I cannot assume everyone knows the Gromov-Hausdorff distance. So let's recall what is the standard setting. And let's start with the definition of isometries that I guess most of you are familiar with. X and Y are isometric if you have maps in both directions, from X to Y and from Y to X, such that they preserve the distances. The distance in the image is equal to the distance of the original points, both for F and for G, and their compositions coincide with the identity. Now, the Gromov-Hausdorff distance answer to the following questions. What if you have two spaces that are not isometric? How far they are from being isometric? How different they are? So we move from this definition to provide a new definition, the definition of the Gromov-Hausdorff distance. Usually it's a characterization, maybe most of you are not familiar with. It's the characterization due to Carlton and Ostrowski. But in this setting, I think that it fits the narrative. So again, so the Gromov-Hausdorff distance between X and Y is at most R. If again, you can construct two maps, not necessarily continuous anymore, like random maps, such that, okay, they may not preserve precisely the distances between points, but they do it up to 2R, where R is the bound for the Gromov-Hausdorff distance, both for F and for G. Now, the third requirement is a bit technical, but you may imagine it as is somewhat like going back and forth is not precisely the identity, but sort of. They are 2R far away once you go from X to Y and come back. You may not go back to the same point, but close to it. It's not precisely it, but for the sake of the presentation, that's more than enough as for understanding. So you can rewrite the Gromov-Hausdorff distance as 1/2 of the infimum all over the set of all functions from X to Y and Y to X of the maximum of the following three values: the distortion of x, which is the supremum for all x and x prime in x of this value, that is the difference between the images and the original distances. The same thing for the distortion of g, and then the co-distortion, which is the mixing factor that whose idea I sketched before. So now let's consider two of the picture that I showed before. How can I construct maps? But in this case, it's particularly easy. You can overlap them. And then for every point in the circle, you can imagine to send it to the closest dot of the other space. In the other direction, if you pick any point, you can project it to the to the circumference, to the circle. And so you have defined two maps. Of course, they are not continuous, but nevertheless, they have bounded distortion and bounded co-distortion. Let's move on. So let's try to formalize what do I mean by chromatic metric spaces. So a chromatic metric space is a data set, a metric space X, and a coloring function, which is a map from the space, from the data set, to the set of natural numbers, which you should imagine as a set of colors of your palette. So most of the time I will work with two colors because it's already interesting enough, but of course you can do the same things for three colors. You can do the same thing for several colors. You can as many colors as you want, enough to color the clothes of Arlequin, which is a stock character in the Italian comedy of the 17th centuries, whose attire is well known to be extremely colorful. So we are interested in preserving most of the properties of the Gromov-Hausdorff distance. Why? Because it's nice, because we want to, because it has nice properties and we'd like to extend them. So there is no need to revolution everything. Let's just try to tweak the definition. And looking at this example, you may think, okay, in the top two drawings, they look very much alike. The Gromov-Hausdorff distance should be close. The two at the bottom, actually, they look a bit different because of where they have red and blue spots. So the intuition would be, okay, I want to diversify these. If colors are involved, it should distinguish more shapes. And so where can I act? Well, I can restrict the set of maps that I'm allowed to use. And this immediately will increase the Gromov-Hausdorff distance. Because if you have an infimum over a smaller set, then you will have a higher one. Okay, first attempt. Let's try. First annotation, because of course I prepared the slides and then I forgot to say who is X and who is Y. So let me state it once and for all. Whenever you say chi, its data set, its underline, its domain is X. If you see psi, its domain is Y. So first attempt, let's require that the two maps respect the colors. What do I mean by that? They have to map n color points to n color points. In this example, our red point here has to be mapped to a red point, cannot be mapped to a blue point, which was actually the map that allowed us to say that the Gromov-Hausdorff distance between the monochromatic setting, the monochromatic shapes was small. And the same for blue. Any blue point must be sent to a blue point. This seems to be reasonable. It respects the colors. I may argue that it's a bit restrictive for some settings. So let's consider three shapes. Again, our Arlecchino. And suppose that in some way we are able to detect that there are some particular features external of the body. For example, this is something else. This flower is something else. This bat is something else. So I want to keep this information. I want to use this information before comparing these shapes. So immediately you can color the three shapes by saying, okay, you have red colors for the body and blue colors for these special features. However, if you do this, there is no map going from the middle figure to the third figure, because the third figure doesn't have blue points. So you are in a situation where the blue parts, the blue points, are additional features that if they are in a shape, you may want to preserve them. But if they are not in a shape, it's not really that relevant. The blue points are relevant only in relation with the red part. So in this case, we couldn't use this Gromov-Hausdorff distance, this first definition of the Gromov-Hausdorff distance, the chromatic Gromov-Hausdorff distance, to compare these objects. This is a more generalized situation. Again, you have immediately infinite Gromov-Hausdorff distance. There are no maps if you don't use the same set of colors. We want to try and do something a bit more general, introducing the C-constrained Gromov-Hausdorff distance. What is C of the C-constrained Gromov-Hausdorff distance? C is a family of subsets of N, subsets of colors. So you have to imagine it as a family of constraints. Each element of C, in C is a bunch of colors. And you force that your maps are C-constrained, which means that they respect those combinations of colors. Sigma color subsets are sent to sigma colored subsets. By sigma colored subset, I mean the subset of points that are colored with colors in sigma. Let's go with an example to just try to understand a bit more what's going on. So we have three colors, and we have a constraint set: red, red-blue, and yellow. What does it mean that the map between them is C-constrained? Well, the red points must go to the red points, are forced to go to the red points. The red and blue points are forced to go to the red and blue points. This actually, you see immediately the difference between with the previous setting, because now a blue point here can be collapsed to a red point. There's nothing that can say that says that blue must go to blue. So it's a bit more flexible. And third, yellow must go to yellow. So we can play with this family of constraints. Different family of constraints may be applicable in different scenarios, may force different kind of behaviors. If you start with the discrete constraint set, which are like all the singletons, all the colors must be preserved, well, you recover the naive definition that I provide you at the beginning, like the first attempt, as I called it. So 2 and 3 are not comparable with 1 and 4. However, if you choose a different constraint set, red, blue, red, it means that red must go to red. Therefore, if your shape doesn't have red, it's not comparable with those that have red, that use red. And blue, red. Blue is free to roam around and to be connected to red points. This is actually the situation that I described before with the three Arlequins shapes, now I can compare them because either the flower or the bat can be collapsed to points in the body of a shape. There is the symmetrical one. You can have blue, blue, red. Blue must go to blue. Therefore, for the shape number 4 is like it works in it plays in a different championship. Can we actually compute something? Well, we already know that already for the Gromov-Hausdorff distance, that's a big no if you think about computing as in like, oh, let's feed these shapes to a program and let it run and it will give me an answer. But we can say something. Upper bounds for the C-constrained Gromov-Hausdorff distance. Well, again, if as soon as you find 2 maps, you immediately have upper bounds. They may not be the best possible choices of maps, but still they provide you an upper bound, an estimate of how big the C-constrained Gromov-Hausdorff distance can be. But what about lower bounds that are usually a bit complicated to find? Because I mean, you cannot, in general, look for all the possible pair of maps. So let's start with some observation. Let's take the example that we used before. And since the maps are red constraints, it means that the restriction of the map F to red points is well defined, because a red point must go to a red point. So it's well defined as a map. And the other way around, same for G. The restriction of a C-constrained map to red points is again well defined. And it's not too complicated to notice that the distortions and co-distortions of the restrictions are bounded by the original distortions and co-distortions. You have fewer points to compute the distortion, to compute the suprema. And so in particular, you have that the Gromov-Hausdorff distance, the usual Gromov-Hausdorff distance between the red data sets is bounding from below the C-constrained Gromov-Hausdorff distance between the chromatic metric spaces. This can be generalized. It works for all constraint in the constraint set C. So for every sigma, the C-constrained Gromov-Hausdorff distance is lower bounded by the usual Gromov-Hausdorff distance between the sigma colored subsets. How useful it is. Well, you can actually use it to provide interesting lower bounds in some settings. Let's consider these following two metric spaces. Well, if you look at just the red parts, the diameter, you can bound the I'm working with the discrete constraint set, meaning red must go to red, blue must go to blue. Good. So the C-constrained Gromov-Hausdorff distance between the two chromatic metric spaces is bounded by the difference in the diameter of the 2 red parts, because of the stability result of the diameter that I recalled at the beginning. And so since the first diameter is 4r, the second diameter is r, the chromatic, the C-constrained Gromov-Hausdorff distance is bounded by 1/2 of their difference. Not always this family of lower bounds help. Let's consider the following 2 chromatic metric spaces. They look somewhat different because you swap positions of the red and the blue parts. However, if you forget about colors and just consider them as metric spaces, they are the same object. If you consider the blue parts, they're again the same object. They are isometric. No bounds provided. If you consider only the red parts, again, no help. So we need to construct some invariants that captures the relationship between two colors. So let's consider the following. The circumradius, red, blue. It's a bit heavy, the notation, but in a nutshell, what I'm doing, I'm looking for the best possible center, red point used as a center for which you can grow a ball of a minimal radius that then can enclose all the blue part. In this case, by construction, actually, if you, at this particular point y can see all the blue part at distance at most r. Now let's go to chi. Let's see what happens in the other space. Can we compute the circumradius? Well, no matter where you place the center of a ball of radius r in a red spot, you cannot you cannot contain the entirety of the blue portion. You actually have to increase the radius up to a certain threshold in order to include it. So now you can show, it's also a bit more generality, but this idea of circumradius is stable with respect to this chromatic Gromov-Hausdorff distance, the C-constrained Gromov-Hausdorff distance. And so again, you can use it to bound the C-constrained Gromov-Hausdorff distance from below. This is 1/2 the difference between the two circumradii. This, as for computations, let me quickly go through some properties, some a bit more general properties of the C-constrained Gromov-Hausdorff distance. So you have this constraint set. I haven't talked a lot about it. You have a lot of freedom in choosing it, depending on your special needs, on your particular needs. But we have to notice that some constraints are implied. You choose a set of constraints, and maybe it's not fully describing the strength of that constraint set. For example, if you bind that green and yellow points must go to green and yellow points, and green, red, and blue points must go to green, red, and blue points, you are forcing, even without explicitly saying it, you're forcing the green points to go only to green points. As long as they go to somewhere else, they contradict one of the two constraints. This is an example to show that C forces the intersection between constraints. And similarly, C forces union of constraints. This is even easier to imagine that if you force red and green to go to red and green and blue to go to blue, then blue, red, and green, guess where they can go? Either to blue, red, or green. In general, you
can I ask a quick question?
Yes, sure.
So each point has only one color, right? I can't have a point in my
sorry. My bad. These are not metric spaces. These are the constraint sets.
Mm-hmm.
It's just a representation of like 0, 1, 2, 3 in N. So like the colors and the
No, I understand. But for example,
okay,
you
sorry.
can't have a data point labeled both yellow and blue.
I'm specifically forbidding it. You cannot. I mean, maybe something can be done, but in this setting, I cannot label a point with two colors.
Right. Yeah.
Sorry, thank you. So you can actually prove that the generated Alexander topology, which is the closure under arbitrary unions and intersection of your set C, precisely describe the strength of your constraint set C. Just a quick mention, and some more properties. Let's start with basic ones. Symmetry and triangular inequalities. We have them. I mean, almost everything is for free because we have it for the Gromov-Hausdorff distance. a bit more refined argument is needed to show that if you restrict yourself to compact situations where everything is compact, the data sets and all the the C-colored subsets are compact, then this infimum is actually achievable. It's a minimum. There are two pair of maps with the best possible distortion and co-distortion. And this observation can be used to prove that if you have two compact, again, chromatic metric spaces that are distance 0, then they are strong isometrically, they are isometric, and also like their restriction of the isometries to sigma color subsets are again isometries. No worries, you don't have to work with maps. There are also characterization. We can provide characterization, the classical ones, so to say, like via correspondences or via some kind of isometric embeddings into a common space where you compare the objects with the Hausdorff distance. Again, there is a bit of tweak that you have to work a bit the definitions, but everything follow into place. Before moving on the very last part, let me just quickly talk about chromatic metric pairs. What do I mean by that? So let's start with two objects, two chromatic metric spaces. Well, how you evaluate them, how similar you think they are, may change as soon as I tell you that they live in different ambient spaces. This is, of course, absolutely known in computational topology. I mean, the ambient check complex is precisely this. It's like taking account of also the alpha complex. I mean, in several situations, you need to know where these points live. So we can extend the definition of chromatic metric space to chromatic metric pair. It's basically a chromatic metric space embedded into an ambient space, A. Previous case is the plane or just a square. The second case is the torus. And you can extend the definition of the C-constrained Gromov-Hausdorff distance also in this setting by saying, okay, I want pair of maps between the ambient spaces that are C-constrained, and also they need to send dataset point to dataset points. Everything works. All the things that I've mentioned before works also in this setting. All the things that I will talk about in the next section will work in this setting. I just restrict myself to chromatic metric spaces for the sake of simplicities. But you can add the ambient space, no problem. So let's talk about the six-pack and its stability. So what is the six-pack? It's they are 6 persistent diagrams that were introduced by Sebastiano, Ondřej, Herbert, and Morteza to detect the relationship, homological. I mean, with an eye on homologies, the relationship between colored points or points that are labeled differently. And so, for example, they wanted to see the difference between these 3 loops. The first one is empty. In the second one, there are a bit of orange points inside, but leaving like quite a consistent chunk of white space. The third one is a bit more mixed. To do this, again, they study it with 6 different persistent diagrams: kernel, relative, co-kernel, domain, image, and codomain. And they relied on previous work to show that immediately show that these 6 persistent diagrams are stable with respect to the filtering functions. If you want to know more about this stuff, Ondřej gave a nice presentation in the same venue about this whole chromatic topological data analysis. Also, it showed a bit of code, so how you actually compute these diagrams. What I would like to focus on is that we can show that the six-pack is stable with respect to the C-constrained Gromov-Hausdorff distance. So it's a generalization of their stability using our geometric approach. We need a bit of definitions to understand what's going on. What the heck are these six-packs? At least a bit of intuition, a few definitions. So let's start with the check complex. And when we construct, here's the definition, and then we construct a subcomplex of the check complex depending on a finite dimensional simplicial complex with vertices in N. Basically, you save all those only those simplices that are colored, those vertices are colored according to gamma. Let's go directly to example. 2 colors are more than enough. So what if gamma is the interval, is the segment that connects blue and orange? Well, then both triangles are labeled have vertices that are either blue or orange, so they live inside this subcomplex. It's actually precisely the check complex, but this is just because we have 2 colors. What if you take only the blue vertex? Well, in the blue vertex, if you choose delta, the blue vertex, then this triangle here, all the vertices are blue. Fine. That's a simplex. This other triangle, though, the vertices are both orange and blue. I will discard it. I'm not taking it. It's pretty easy to imagine that if delta is smaller than gamma, it's not just in this particular situation, but in general, you have an inclusion of simplicial complexes. And so this combined with changing the parameter R, you have somewhat a ladder. So you have 2 parallel filtrations with all these arrows are inclusions. So studying this ladder and applying homology functor, and then you have 6 persistent modules. You take the persistent diagrams, and here is your 6-pack. So what can we do? What can the C-constrained Gromov-Hausdorff distance say about this setting? Well, let's start with 2 chromatic metric spaces and the simplicial complex with vertices in N that we worked with before. Then there is a way, I will not go into details, but there is a way to construct a suitable constraint set, C, depending on that simplicial complex. And in this way, if you start with a C-constrained map from chi to psi, then this map can be immediately induced to the subcomplexes. There is a cost to pay. You have to increase the radius by precisely the distortion of F. So basically, because you are moving a bit the points. But this can be done. F is just defined. That's why I use the same symbol. F is just defined on the vertices. And this is precisely the definition. It's precisely the same map, the same constraint map. Although, I mean, theoretically, like they are different objects, but it's the same. And if you have also S, another parameter in your filtration, you can do the same thing, adding distortion of F. You can have another map. And since it's the same map we are working with, this parallelogram perfectly commutes. If you add a layer, if you add another simplicial complex as a subcomplex of gamma, then as long as C takes also that one into account, you can construct the same thing. and it commutes also with the inclusion, with the vertical arrows. Everything perfectly commutes. You can do the same thing for a map in the other direction, from psi to chi. And so you have some kind of maps. You have a family of maps in both directions. Since you also have a bound on the co-distortion, these maps, so all the side diagrams of the diagram that you create in that way commute or commute up to contiguity, which means that once you apply the homology functor, everything perfectly commutes. You have an interleaving between the persistent modules, and here is your stability result. So if X is the letter for chi and Y is the letter for psi, for any of the 6 diagrams, you have that the bottleneck distance is bounded by twice the C-constrained Gromov-Hausdorff distance between the chromatic metric spaces. And that's it. Thank you very much.
Thanks so much. So before we get to questions, let's briefly unmute ourselves and applaud for the speaker. All right, questions. I'll start with one. So is there a chromatic version of the Hausdorff distance? Of course, standard Gromov-Hausdorff distance relates to Hausdorff, and you could infamize overall possible isometric embeddings. Yeah.
Absolutely. There is. It's again a C-constrained Hausdorff distance. Basically, so let's work with the normal Hausdorff distance in a less nice way. So there are different formulations for the Hausdorff distance, but in a nutshell, what you do, like for every point in the first space in X, you find a point in Y close by, and the other way around. What you have described is actually a correspondence between the two spaces, which is a relation between the two sets, such that every point in the first one is related with at least one point in the second one, and vice versa. You constrained this correspondence by saying, okay, you have to respect the constraints that I give you. So if you restrict yourself to consider sigma colored and sigma colored subsets, you want that also that restriction is still a correspondence. It's slightly more technical. You cannot do it for all constraint sets. The advantage of working with maps is just like, I give you a constraint set, no matter what, everything follows. Here you need to force that the constraint set is closed under intersection. It's not big of a deal because you have that they have the same strength. If you take the closure under intersection, has the same strength that is the original constraint set, but it's a technicality that you have to take into account.
More questions. So I have another one. So you explained this nice stability at the end involving Czech complexes and the different chromatic variants thereof. Could you say what the original stability result due to Ondřej and Herbert and Sebastiano was? So they were only looking at stability with respect to a filtering function. Can you say what you mean?
Yes. So basically, you have your point cloud, and then you take the they use the alpha complex, but whatever complex you are interested in, Vittori shapes, whatever, and then you label the simplices by their size, like when they appear in the filtrations.
Yep.
So now you work with these. So suppose that you have two filtering functions from the same set of points, or like so there are a bit of restriction in that sense. But you work with the same so you have two filtering function, and then you compare the two filtering functions with the supremum metric, and say if your two filtering functions are similar in that metric, then also the bottleneck distance between the diagrams are small.
Right, but it's sort of like a fixed domain, fixed simplicial complex on which your two different filtering functions live.
Yeah.
Correct. More questions? I have one more. So the ambient setting, was your coloring on the ambient space or on the sort of the data set subset of the ambient space?
The data set. The data set has to be colored. It was motivated by the chromatic point clouds that that Ondra, Herbert, Morteza, and Sebastiano work with. Over there, you have colored points in a Euclidean space or in a cube, whatever you are living in. So the data set is actually the color point. And then you have where these points live, the ambient space. So you don't want to color there is no need to color the ambient space. You just color what you are interested in, just the data set.
Right. Mhm.
And in the monochromatic case, I mean, there is no need to color the data set in principle. If you have like of one color, let's say black, all the points, then this stability here can be used to show that the stability of the ambient check complex. Of course, this is not the only way to achieve the result. There are other ways to prove the same fact, but that's another application of this technique.
Dave, please go ahead.
Uh, let me just turn my video on. It seems to be for some reason it looks like my video isn't working. Is it working?
No, not right now.
Okay, I'm sorry about that. My question, it's not particularly well formed, but it seems that you could talk about a data set with many, as you are, many different colors. You could ask questions about the mixing of the data over time. So you suppose you had a dynamical system and you have mixing of the two colors. Can you get at that mixing using this chromatic Gromov-Hausdorff?
Mixing, you mean like moving? First of all, thanks for the question. I mean, that's a fantastic direction to explore. But let me try to understand a bit better what's your point. Like by mixing points, you mean the points move around the space? You're, for example, in the plane, and you start with a certain configuration, then you move
Right,
the
right.
points. Okay.
That's what I was thinking about. Suppose you had uh, your data consists of two different colored objects, and initially they're separated. At some point, you have something like diffusion going on, so they spread and interact. Does that show up here? Because after all, if depending on what your sets are, if you don't care about the colors, then there's nothing going on. But if you care about the colors, perhaps there is something going on about the distances between the sets. The two sets now, the X and the Y, would be the same set and then at a later time.
That's a terrific direction. I mean, that's super interesting. I wonder. So, in a sense, it can be used. I wouldn't advise it. I mean, unless on a theoretical viewpoint, because if you want to, for example, like sample over time what's going on and then compute the Gromov-Hausdorff distance for all these timestamps, well,
Yes.
that's already complicated
Right.
to
Right.
do it just for two timestamps. I can hardly imagine what's going on for more. It doesn't mean that there is no possibility for any theoretical result, like stability of some kind of the orbit or whatever. These kind of approach, saying that like a certain group of points, well, they move, but because of some dynamical properties, they don't move as much to ruin the Gromov-Hausdorff distance. Or if the Gromov-Hausdorff distance is small, then all these orbits must be small. Something along these lines maybe can be done, but I don't know enough to about also what happens in the standard setting without colors, if the Gromov-Hausdorff distance was ever applied in that setting.
Mhm. Okay.
But that's definitely a super interesting direction to explore.
Okay. Well,
Thanks.
thank you. I appreciate it.
All right, why don't we end the public portion here? So thanks so much again, Nicolò.
Thanks to you.